Okay, so picture this. Inside a pristine, high-tech clean room, there's a machine about the size of a city bus, and it's doing something that sounds completely impossible. 50,000 times every single second, it forges a star. It creates thousands of tiny, controlled supernovas, each one about 40 times hotter than the surface of our sun, and it's doing all of this to save the one law that has defined our entire digital world for more than a half a century. This is the story of that machine, the one that saved Moore's law by literally bending the laws of physics to its will. Now, this isn't some science fiction concept. This is happening as we speak. This machine is building the chips that are in your phone, your computer, your car, everything. And according to the people who poured decades of their lives into creating it, this is, and I'm not exaggerating here, the single most complicated piece of commercial technology that humankind has ever put together. And yeah, it comes with a price tag to match. A single one of these machines costs $400 million. So you have to ask yourself, what problem could possibly be so huge, so fundamental, that it would require humanity to pour decades of research and literally billions of dollars into something this extreme? Well, the problem was a crisis that was looming over the entire tech industry. The engine of progress, the very heartbeat of Silicon Valley, was about to slow down and grind to a halt. We were staring right at the end of Moore's law. For 50 years, Moore's law was the reliable rhythm of innovation. See, back in 1965, Intel's co-founder Gordon Moore, he noticed this pattern, and it pretty much became a self-fulfilling prophecy for the whole industry. Every 2 years, our gadgets got exponentially more powerful. It's the reason the phone in your pocket right now has more computing power than all of NASA had for the Apollo 11 moon landing. Think about that. The secret to this whole thing was, on the surface, beautifully simple. Just keep shrinking the transistors. Smaller transistors mean electrons have less distance to travel, which makes the signals faster. Plus, you can cram billions more of them onto a single piece of silicone. But after 5 decades of just relentlessly shrinking things, this incredible engine of progress was about to slam into a fundamental wall of physics. And here's where we get to the heart of the problem. To create these incredible microscopic cities on a chip, engineers use a process called photolithography. Just think of it like photography, but for etching patterns onto silicon. They were using 193 nanometer deep UV light. But the problem was, the tiny transistor features they needed to print were becoming smaller than the light's own wavelength. Imagine trying to draw a microscopic line with a paintbrush that's physically wider than the line itself. It's not possible. So to keep Moore's law alive, the industry needed a new paintbrush, a completely new kind of light. And it was one that most of the world's top scientists believed was impossible to harness for manufacturing on any kind of commercial scale. This was a desperate leap of faith into the unknown. The idea was to jump to a much, much shorter wavelength, extreme ultraviolet light, or EUV. At just 13.5 nanometers, it actually behaves more like a soft X-ray than what we think of as light. In theory, this incredibly fine paintbrush could draw the impossibly small features that the industry desperately needed. But in practice, well, working with EUV light was an absolute nightmare. You see, EUV light is basically the diva of the electromagnetic spectrum. It gets absorbed by everything. Air? Nope, forget it. The entire machine has to be a giant, perfect vacuum chamber. The glass lenses you'd normally use in a microscope, they just soak up the light like a sponge. So the only way to guide this light was with a really complex system of mirrors. And not just any mirrors. We're talking about mirrors that would have to be the most perfect, most reflective surfaces ever created by human hands. The skepticism from the scientific community was crushing. When a Japanese scientist, Hiro Kinoshita, first presented his successful experiments with EUV all the way back in 1986, people didn't just disagree with him, they flat out refused to believe him. They dismissed his groundbreaking work as nothing more than a big fish story. And he wasn't alone in this. A few years later, an American scientist at a national lab, Andrew Harvey-Luck, proposed a similar system for building ships. And the response from his peers? Well, in his own words, he was literally laughed off the stage. The world's experts thought this whole idea was a joke. But even if they could solve all these problems, there was one challenge that was bigger than all the rest combined. Because even if you could build the perfect vacuum and the impossible mirrors, you still had to solve one colossal problem. Where do you get the light? EUV light doesn't really exist naturally on Earth in any usable form. To create it, you'd have to do something that sounds crazy. You would have to forge a star. The solution they finally landed on was just audacious. It was almost unthinkable. The engineers had to figure out how to create and contain a tiny, stable, and unbelievably powerful plasma source inside the machine. A plasma that would reach temperatures of over 220,000 degrees Celsius, which is about 40 times hotter than the sun itself. So how on earth do they actually do it? It's this breathtakingly precise two-step dance of light and metal. First, a tiny droplet of molten tin, smaller than the width of a human hair, is fired into the vacuum chamber. Then, a low-power laser, the pre-pulse, zaps it, instantly flattening it into a perfect little pancake. Then, just microseconds later, bam, a massive 20,000-watt laser, the main pulse, obliterates that tin pancake. It vaporizes it into that super hot plasma that finally emits the precious UV light they need. And here's the part that is really hard to wrap your head around. This isn't happening once a minute or even once a second. The machine performs this perfect two-shot laser strike on a brand new tin droplet 50,000 times every single second. And it cannot afford to miss. This whole process is so extreme that one of the lead scientists on the project realized that the physics formula they were using to describe the energy blast from each droplet, well, it was the exact same one used to describe exploding stars. So it's not just an analogy. They are literally creating and controlling tiny, repeatable supernovas inside this box over and over and over again. So, after 30 years of fighting skepticism and solving one impossible problem after another, the machine exists. It's real, and its final specifications are the reason we get to hold the future in our hands today. A temperature of 220,000 degrees Celsius, contained and controlled inside a commercial product that runs 24/7. It's an engineering achievement that really does border on magic. And what about those impossible mirrors? Well, they are the smoothest objects humanity has ever made. To give you some perspective, imagine one of those mirrors was expanded to be the size of our entire planet. On that Earth-sized mirror, the biggest imperfection, the largest hill or bump, would be less than a millimeter high. That's what true atomic level smoothness looks like. And the precision of the final output? The machine stacks hundreds of layers on top of each other to build a single chip. The maximum allowable error, the wiggle room between any two of those layers, is just 1 nanometer. That's about the width of 5 silicon atoms. It's a level of accuracy that's almost impossible to even comprehend. So why does any of this matter to you? Because this machine, which was born from an idea that was literally laughed off the stage, is now completely indispensable. Every single cutting-edge processor, every advanced graphics card, every chip that makes our modern world possible, it's printed using this technology. It is the invisible but absolutely essential engine of our digital lives. And this whole incredible story, it leaves you with a really fascinating thought. Progress, it seems, doesn't always come from reasonable people who just accept the world as it is. It comes from the unreasonable ones, right? The stubborn pioneers who just keep going in the face of impossible odds. It really makes you wonder, what impossible-sounding idea today is just waiting for its own moment of unreasonable persistence to make it real?